Security is hard.
Nothing to do with security.
Whatever. Felt like I do security. It feels hard still. Who said nothing to do with security? You did. Oh, it's one of our own guys who did.
PowerPoint.
That's crap.
PowerPoint, right? I'm saying.
I know. I was looking for some office certification or something so I can figure out how to use Word again. All right. So 179 slides last class, only 134 today. But you'll see that a lot of the slides today are kind of just diagrams of things that I talked about, right? So we'll talk about packets and segments and frames and all that stuff, right? And they'll just be pictures of those things, so it helps make more sense. So don't be intimidated by 134. I think the class before last, we only had like 107 or 87 or whatever. I did get the slides out before class today. They were done by like noon. Did anybody know that? Okay. So you guys have the slides. If you want to make notes on your own slides or whatever, feel free to do that. We'll start kind of the same way we start every class, just 5 or 6, from the book. Quiz questions. The first one, what type of sprinkler system would be best for an art gallery? D. Wet pipe, dry pipe, deluge, or pre-action?
Dry pipe.
Reaction.
D.
Pre-action. Yeah, because at least with a pre-action, I have a chance to deactivate the alarm. Because two things have to happen. Maybe a smoke detector went off, and that would then fill the pipe. The other thing might be the melting of the valve. You know what I'm talking about. Which would then open the valve, let the water come out. So I have time to react to a pre-action. The deluge, the water's already in there, and it just dumps in a huge, it's a deluge. That's what it is. Dry pipe, there won't be a second activation. It'll be just that the pipes are they're not full. We would use that in places that freeze a lot, is where you'd see dry pipe, and then wet pipe, same kind of thing. There's no second action. So the right answer here would be the pre-action. What is the primary drawback in using dogs as a perimeter control? Training, cost, liability, or appearance?
Liability.
Unless you have a really ugly dog, then it'd be appearance, right? Yep, liability, because dogs bite people and people don't like to be bit, I guess. The RSA algorithm is based on which one-way function? So RSA algorithm, if you remember, that's a asymmetric encryption algorithm. And we only covered 2 of those. We covered the discrete logarithm, and we covered the prime, really huge prime numbers. So you can get rid of elliptic curve, and you can get rid of frequency distribution. That's not even an algorithm. So which one would it be then? Which one of those 2? So this is just a memorization, knowing which one it is. D? D is right, yeah. You're surfing the web via a wireless network, probably public Wi-Fi, and somebody's using an ARP poisoning attack and mimicking all your traffic and seeing everything that you're doing. I didn't say that, but anybody ever done an ARP poisoning attack? They're pretty easy. What was that damn tool? There was a tool that I was talking about last week. I forgot again. It's really easy to do an ARP poisoning attack with the same tool that you can look at hash functions in. Do you know what I'm talking about? It's a Windows tool. It's been around since like 98, 99. Anyway, we should do an ARP poisoning attack. Maybe we'll do that in one of our last classes to show you how easy it is to do. Your wireless connection becomes, and I can explain it to you, because today we're going to talk about networking. I can explain to you how an ARP poisoning attack works. That'll be fun. Your wireless connection becomes unreliable, so you plug into a wired network to continue surfing. While you change physical networks, your browser required no change. What security feature allows this? Abstraction, hardware segmentation, layering, or process isolation? Layering. Yep, layering. Abstraction is a function of layering, but that's not what allows this to happen.
Cane enable?
Cane enable. There you go.
At some point I had to get
Anybody ever used cane enable before? Oh, it's a cool tool. It's kind of a Swiss Army knife little tool. It doesn't do really super awesome things, but it's kind of fun to play with. It's free. Can't enable. Thank you.
Scary how many free tools.
That was driving me crazy because last Thursday I couldn't, whatever day we were here last time, I couldn't.
Now there's a bunch that were not it.
Yeah, so Can't enable is a really easy tool to do an art poisoning attack with. Criminal deduces that, there's a key word, deduces that an organization is holding an off-site meeting and has few people in the building based on the low traffic volume to and from the parking lot and uses the opportunity to break into the building to steal laptops. What type of attack has been launched? Aggregation, emanations, inference, or maintenance hook. So he's inferring that there's not people, and now's a good time to attack because there's nobody in the parking lot or whatever. So yeah, it's an inference attack. Not a technical one like the one we talked about in the book, but inference nonetheless. What is the most important goal of fire suppression systems? This one should be easy, right? I put this one, I mean, it was in the book too, but this one on purpose, because you gotta, that's always the answer. All right, that's it. Now we're on to domain 4, communication and network security. How many people in here are network people? Yeah, so this will be so easy. I'm not strong in IP version 6. Anybody in here strong in IP version 6? Because most of us haven't. I'm not
I was going
either.
to call liar if anybody raised their hand. Nobody uses it.
Because IP version 6, yeah, it's rare to find somebody, unless you work at an ISP or something and you're running a dual network. What do they call it? Dual, a system that can translate between IP version 4 and IP version 6. I don't remember. But anyway, that's the only part of this whole, any of these slides that I'll have to actually, you'll actually have to look at the slides and to memorize, because IP version 4 stuff is really pretty straightforward if you're a network person. If you're not a network person, you'll just have to memorize a lot of this stuff. You'll just have to, it's all logical. It all fits together nicely. That's just the way it is. So network architecture, design, secure network devices and protocols, and secure communications. We're going to get through not this entire domain tonight. We'll get through about half of the domain tonight. So we'll get into network devices and protocols. We won't get into secure communications. Secure communications is when we get back into the SSL again, and we talk about TLS, and we talk about IPsec, and all those things, which is should tie in well with what we had a few classes ago. When we talked about IPsec, and we talked about transport mode and tunnel mode and authentication header, encapsulating security payload, and all that other stuff. That stuff will make a lot more sense on Tuesday when we get into that again. But we're not going to cover secure communications today.
Dual stack.
Dual stack, thank you.
To Doug Online.
Thank you to Doug Online. So dual stack is one of those systems that can run IP version 4 and IP version 6 and translate between the two. So starting on page 218, or 19, if you're in the book, that's where we're at. So network defense in depth, I added something into this slide that you won't see in the book. It's one of my favorite references when you talk about, when we do a lot of attacks today, we just assume that we've already got into your perimeter, right? We've gotten past your perimeter, because that's usually pretty trivial, right? The ways you can leverage human beings and their behaviors, get them to fall for a phishing attack, or get them to open up an attachment or download something. So what can I do once I'm already inside the network? That's what network defense in depth is about. That's where we talk about things like segmentation, isolation, right? Those are two different things. Segmentation in the most traditional sense is where we're just using VLANs to segment a network. What we're doing is we're breaking up broadcast domains, and we'll talk about broadcast domains and collision domains. But isolation is when I'm using a packet filtering device like a firewall between network segments. And network isolation, anybody in here cardholder data environment PCI work, right? So the rule of thumb in PCI is if something that's considered outside of scope, if the complete compromise of that system can affect the security of something inside the cardholder data environment, that thing is also in scope. Does that make sense? And the way we would bring those things out of scope is we'd use isolation. This reminds me back of the target breach, right? The target breach, and I did all that crap that I did with the target breach. They had, from the corporate network into the cardholder data environment in the stores, they had port 3389 open. That's not isolation, right? 3389 is used for RDP, remote desktop protocol. So a complete compromise of something on a corporate network can very easily lead to a compromise of something in the cardholder data environment because it's just RDP, right? One of my favorite things is, it's not a reference in the book and it's not testable, but if you want to know more about obstructing an adversary, so somebody who's actually in your network, keeping them away from everything in your network, there's a good NSA document here with some good guidance. That's the NSA methodology for adversary obstruction. But you understand the defense in depth, right? If something is compromised, can you contain it so that it can't just continue to propagate and compromise other things? All kinds of different strategies for defense in depth, but that's the point. That's a picture of that thing, that document, and it is good reference. It's another diagram of what defense in depth would look like, things and technologies that I could put in place to implement defense in depth for the test. You're not going to have to worry about all of that. Understanding the concept of defense in depth and maybe some controls that you could put in place to contain somebody. Compensating controls are often used when you refer to defense in depth. Now I got to lift, so this is how I talk now. Too many S's. What?
Your head.
Yeah.
You'll be able to stop doing it.
You just did it, didn't you? Stop. Right. So, any questions on defense in depth? Now we're going to go with some fundamental concepts. Some of these fundamental concepts at this point will just be like spotty fundamental things that you'll just have to memorize, right? They'll come together when you realize kind of how a network all works together. So this is one of those spotty things. Different types of communication on a network: simplex, half duplex, and full duplex communications. So simplex is just a one-way communication, right? And that's a very good analogy. It's like your car radio. There's no communication back from your car to the radio station. It's just one way. Half duplex is back and forth, but it's not at the same time. So half duplex would be, you say something, you reply. You say something. The walkie-talkie analogy works good for half duplex communication. Then full duplex communication is simultaneous communication back and forth. It's like us talking when we have a conversation, right? We just continue to talk. So you'd have to memorize, the difference between, simplex, half duplex, and full duplex communications. Do they still set up, I haven't set up a router or a switch in a long time. Do they still have auto negotiation for duplex? Okay, because we always had to set those because it never negotiated correctly. I don't know if you still have to do that.
Probably a smart idea.
It is a smart idea. It's a smart idea from a security standpoint to set everything that you can set and not leave anything to default. It's just a rule of thumb. Baseband and broadband communications, this is just what can go across the medium in the number of channels. So a broadband communication has multiple channels. So broadband communication would be like at home, where I've got a cable, maybe my cable provider. I can run voice, I can run data, I can run audio, video, whatever, all on that same media, because there's multiple channels running in that broadband communication. Whereas baseband communication is just a single channel. You don't run multiple things on a baseband network. Now you can use a baseband network with higher level protocols to run different applications. That's a little bit different than just the base communication that takes place on the. So Ethernet is a baseband network, but that doesn't mean that I can't run audio or video or multiple things on a baseband network. It all just goes in one channel. Does that make sense? It's higher level protocols, it's higher level things that happen on the Ethernet network, because Ethernet runs at layer 2. When we talk about the OSI model, layer 3 and 4, primarily layer 6 and 7 is where I can run multiple things on that same baseband network. But understanding that baseband single channel, broadband multi-channel for the test. Other concepts, analog and digital. Analog looks like that. It's on a wavelength, right? It's not discrete. A digital signal is always discrete. It's always 0 and 1, yes, no. It's flipping switches, right, is how digital communication works. Analog people are analog, right? That's why they're so hard to secure. Like technical stuff is really easy to secure. as long as you don't have people, right? Because when you start putting the analog stuff in there, you never know where people are at on a wavelength. They're not discrete. They don't, you look at people and you're like, why the hell did you do that? Right? There's no on or off. It's somewhere in between. Radio waves are analog. Microwaves are analog. Digital, the electrical pulses that go on an Ethernet, a copper cable, or the flashes of light on a fiber optic network, that's all digital. They're discrete, on and off. Make sense? All right, you'll need to know these. Now, I don't think I've ever used the term GAN and rarely PAN, but it's pretty logical, right? LAN, local area network, wide area network, metro area network, global area network, and personal area network. It's just, the scope essentially of the network. A personal area network would be like your Bluetooth stuff, near field communications. Sometimes, I suppose you could call those personal area networks. Typically range 100 meters or less. Local area networks we used to separate local area networks by floor, but now it's more like by building, and now really it's more by the technology that's used, right? In a local area network, typically you're running Ethernet. Typically it's an RFC 1918 IP address, which is the private IP addressing. Right? That's a local area network. When you start talking about routing, then you're talking more either metropolitan area or wide area networking. Metropolitan area network would be over a metropolitan area. So if FRSecure had another office in Edina, another office in Minneapolis, and we were connecting those offices together, we could say that that's a metro area network. Wide area networks, wider geographic location. If we had an office in Boston, that would be more of an example of a wide area network. There's different technologies that are used on wide area networks and local area networks, right? Anybody still using like frame relay? I just dated myself. I did a lot of frame relay and a lot of ISDN work back when I was, strictly a networking guy. Anybody using ISDN?
Token ring.
Seriously?
Then token ring.
Token ring, yeah.
Replace.
I can tell you one of the hardest networking troubleshooting things I've ever had to do was a token ring network at IBM. Every time, we couldn't figure it out. But long story short, the network would have intermittent outages, and we could never figure out why we were having these intermittent outages. We checked cabling, we did everything. Well, turned out that every time there was one bathroom, and every time somebody used this women's restroom and flipped on the light, the cable ran. We didn't realize the cable ran over the fluorescent light, and so it would take out the network. Right, the token could no longer pass from one to the other. It took us forever. It took us like a week to figure out why the hell does the network keep going down? Because it wasn't one of those like bathrooms that was like used all the time. It was one of those kind of bathrooms on a floor on the side somewhere. And then global area network. So here in London, right? If those networks are connected together, they would be a global area network. Circuit switch network. So there's two types of networks here. There's a circuit switch network and a packet switch network. A circuit switch network would be that we set up a circuit and then all communication takes place over that circuit. That circuit remains nailed up until the communication is over. There's switched virtual circuits, private virtual circuits. We're not going to talk about that too much. We'll get to that, I think, when we talk about frame relay on Thursday. These are sort of wasteful because whether the communication is taking place or not, or whether the communicating devices are using the entire circuit, it still remains nailed up and you use those resources. Sometimes these are virtual circuits, so the circuit gets stood up by two systems that are communicating together, and then when it's done, it just gets torn down. Sometimes they're physical. It's a point-to-point network where it's physically two devices just using that communication. Dedicated circuit or channel, portion of a circuit dedicated between two nodes, dedicated bandwidth. And a good thing about a circuit switch network is it is more reliable and more predictable than a packet switch network, right? The internet is a classic example of a packet switch network where all your communication gets broken down into little segments or chunks that are called packets, and those packets then just kind of get shoved out on the internet. Some might take this route, some might take that route, some might take another route, and they all have to be reassembled at the other side. That's a packet switch network. There's really no reassembly required in a circuit switched network because it's pretty much a serial type of communication. Packets don't get jumbled up. Does that make sense?
If you want a really good example of the packet switch stuff, you can watch the Magic School Bus Rides Again internet episode.
The Magic School Bus Rides Again internet episode? We'll have to make that a resource. I've never seen that.
Yeah, it's on Netflix. Netflix rebooted the Magic School Bus. And they go over pretty much how the internet works. They're emailing and stuff, and they specifically talk about packets.
Packet switch networks, yeah. Yeah, every router, I mean, there's ways to manipulate, but in general, every router makes a routing decision based on what's the best path to get from point A to point B. And depending on your routing protocol, it could be, bandwidth could be a consideration, round trip timers, I mean, all kinds of other things could be considerations on what's the best path. And you could, potentially, the routers could make a packet by packet decision on the best path, right? And then they all have to get reassembled when they get to their destination or get retransmitted. Layer design, so the same concept applies here that applied when we were talking about systems. This is applying it to the network. The two models, and the only two models you'll have to know for the exam are the OSI model and the TCPIP. Sometimes we refer to the TCPIP model as the DoD model. Those are interchangeable. Yeah, and it's the same kind of encapsulation, abstraction, layering that happens in each of these models. You can layer, and I'll show you, in the class here, how TCPIP layers on top of OSI. And OSI is a conceptual model, right? Meaning we don't actually apply OSI, hard and set into our systems. TCPIP is a little bit different. TCPIP is a suite of protocols that we actually do layer, that we do apply into network communications. Anybody here ever used IPX, SPX? Apple Talk, back in the good old days? IPX, SPX is not one that and I think it was in a book like not all that long ago, but it's not in, I don't think it's in this book, so that's good. IPX, SPX used to be used for the old Novell NetWare stuff. What else did I miss here? Each layer performs a specific function. There is abstraction, so each layer, things that happen at one layer are abstracted from what happens at another layer. Complexity is hidden. Layer 1 is the most basic functions of a network. That's the physical layer, and then it gets more and more complex as you go, up the stack to layer 7, which is the application layer. The difference between models and stacks, one uses actual protocols, the stack uses protocols, the model is just a model. Protocols is rules, so there's all kinds of protocols here in networks, but we also use protocols in communications. When there's an incident response, you should have a communication protocol, who can talk to who and when. Same thing, just applied differently. So the OSI model, the Open Systems Interconnected model, it's a reference model, so it's not applied, like I said, specifically. 7 layers, and I'm going to give you a bunch of mnemonics that you can use. I'm not a mnemonics guy, so I've just always remembered application, presentation, session, transport, network, data link, physical. I don't know the letters that go with that, but you'll memorize that. You'll need to memorize that for the test. Not what I just said, but you can use one of the mnemonics too. Anyway, that's what it was formerly called. I don't think that's testable either. If you want to actually download the actual standard, that's the link you can use to do that. And here are the layers. And it's important to know the data units on the side. So it goes segments, packets, frames. Everything else is above that is data. So the transport layer, that's where we'll lay TCP/IP on top of it. But that's where TCP and UDP live. Those are segments, and then it hands it down to IP. That's where IP lives at the network layer. Then it becomes packets, and packets get broken down into, depending on the transmission media that I'm using, and the data link layer into frames. And then the bits are just the ones and zeros. And sometimes the ones and zeros are sent as electrical signals. Sometimes they're sent as light. Those are the two, most common ways to send it. Why the layered model? There's the reasons. Less complexity, standardized interfaces. It truly is an open system, so it allows multiple manufacturers to play well together on a network. Modular engineering, interoperable technology accelerates evolution, simplifies teaching and learning. Some people would argue that's not true, but it is. Any questions on this? How many people know the OSI model, like the back of their hand? So this is all like, boring. What?
I have to think about it, but
Yeah.
that's true because I don't know the back of my hand very well.
Oh, I do, man. I go look at it all the time when I'm typing and stuff. I'm like, what the hell is that? Sorry, got stuck. There's some mnemonics there. People don't need to see Paula Abdul. People don't need those stupid packets anyway. Please don't teach students pointless acronyms. Please do not take salespeople's advice. Those are all applicable. Use whichever one makes the most sense for you. So starting at the most basic layer, layer one is the physical layer. This is the things that you can touch, right? And this is where you start, with troubleshooting, right? Most network problems happen at the physical layer. The one I just described with the fluorescent light and the cabling going over that, that would be electromagnetic interference that happens at layer one, that it was a physical. Most network things start physical and then work your way up, I guess is what I'm trying to say. Layer one devices, hubs and repeaters, stupid devices that don't make any decisions, they don't make any traffic decisions, they don't make any routing decisions. Repeaters and hubs, the difference between a repeater and a hub, a hub is a multi-port repeater. So a repeater just takes a signal in one end, regenerates the signal and sends it out the other end, right? We'd use a repeater to protect against attenuation, a weakening of the signal over a long course of time. Hubs are just multiple ones of those, right? We don't use hubs, we don't like hubs because there's no logic, there's no security in hubs, there's one big collision domain in a hub. So if you put a hub in a network with any kind of traffic, you're going to see the lights start blinking and blinking more, and then pretty soon the network comes to a halt in a lot of networks because there's no segmentation of that traffic. Everything that goes on the wire goes to everywhere on the wire. Where we do use hubs sometimes is when we're doing like packet sniffers or IDS devices or IPS devices where we actually need to see all that network traffic. That's the only time we want to see hubs and repeaters on networks. 3Com. Is 3Com still around? For some reason 3Com just popped into my head. That was one of my, what? HP bought 3Com. Right, so there's physical binary transmission. Binary means 0 or 1. Right, that's binary. If you're big into TCPIP and you understand, TCPIP version 4 anyway, you would know binary probably really well. You know the 2 to the x minus 2 for the subnetting and supernetting formula. We don't have to do subnetting or supernetting on the test. If you want to know that stuff and you don't know it, we can teach you that later. So the next layer is layer 2. Layer 2 breaks up the collision domain, but we still have a broadcast domain. That means, I'll get into broadcast domains when we talk about layer 3 devices. Things that play on layer 2 devices, bridges and switches, play at layer 2. And there's some logic here now. And the logic is based on physical addresses that are burned into MAC, burned into network cards and other devices. And the logic is, I'm only going to forward the traffic out to the port that it belongs to. And if I don't know what port it belongs to, I'm going to send it out all ports until I learn what port it belongs to. Does that make sense? So there is some segmentation that happens here at layer 2. Handles access to the physical layer, so coming down, and then it'll also, going back up. There's 2 parts to the data link layer. There's the media access control and the logical link control. Sublayers. It's the only layer in the OSI model that has sublayers, logical link control and media access control. That media access control, the MAC, it's the same MAC address, the same kind of function. It's really taking ARP lives there. We'll get into that too. But it's taking the logical address and equating that to a hardware address because computers actually communicate on a network with hardware addresses. Ethernet card and its media access control address are at layer 2. Switches and bridges live at layer 2. There's the two sublayers, the media access control and the logical link control, and their basic functions that they do. A lot of this is memorization. If you don't know this stuff. Layer 3, now we've got more logic. Here we've got, routing, we've got some congestion control, we've got other things that happen on a network. There's also the interface between, we're starting the interface now between individual sessions being set up on a network and that lower level communication at the hardware address. Describes routing, moving data from system on one LAN to another. That all happens at layer 3. Layer 3 is also where we break up that broadcast domain. So understanding collision domains and broadcast domains, I don't know if it'll be on the test, but it's important to know when you're working with your own networks and you're deciding what type of device do I put here. IP addresses and routers are logical. So an IP address is a logical address. That MAC address that was here, that's a physical address. IP addresses are logical addresses. Routers live here. IP version 4 and 6 live here. That's layer 3. Address or best path. That logic. A lot of routing protocols also live at layer 3. OSPF lives mostly here. Routing information protocol RIP lives mostly here. EIGRP lives somewhat here. There's actually a TCP port for EIGRP. Am I preaching? You guys get it? Those of you who aren't network people, am I going too fast, too slow? Is it making sense?
I gotta find my tip. I can't remember. There's a way to figure out which layer they live at. I brought it up last year. I don't remember.
Oh.
Was it?
Hubs, well, you only have 3 layers where you have to remember where things live at, right? It's hubs and repeaters at layer 1, switches and bridges at layer 2, and routers at layers. Well, I guess firewalls
I'll
can
interrupt
span
you
all 4
when I
layers.
figure it out.
Well, I actually have a good diagram for
Okay,
that
good.
too. Layer 4 is the transport protocol, transport layer, packet sequencing, flow control, putting things back together, all happens here at layer 4. TCP and UDP are layer 4 protocols when you map IP, the TCPIP model on top of OSI, because TCP and UDP are not OSI protocols. They're TCPIP protocols, but we're just layering on top there. Resending or resequencing packets, windows happen here. Windows is essentially how much data I expect to receive before I get a confirmation that, they're windows of data. That all happens at layer 4. End-to-end connections, it's layer 4. Network reliability, fault detection. TCP and UDP, we'll talk about the difference between those two in a minute. But that's layer 4. Layer 5 is the session layer. It's easy to remember because it manages sessions. RPCs live here, remote procedure calls. This is a translation between network functions and applications. An RPC allows two applications to communicate over a network. Right? There's a couple of protocols that we'll talk about later, not in this session, but later on we'll talk about Corba. We'll talk about what's Microsoft's one? Can't remember the name of it. Anyway, those things live here at layer 5. Session layer, connections between applications. So before it was connections between, it was sessions on, sessions at layer 4, where we're talking more about setting up the connections. This is more about the applications beginning their communications. Happens at layer 5. That simplex, half duplex, and duplex are all negotiated here. Interhost communication. Layer 6 is all about really all about translation. Translation, encryption, in some cases, compression happens at layer 6. Layer 6, it's taking things from the application and preparing it for the network, and conversely, it's taking things off of the network and preparing it for the application on the other side. Data conversion, characters such as ASCII, GIF, JPEG, those are all compression formats for images. All that stuff happens at layer 6. More good stuff. And then layer 7 is the application. That's the interface with the human being usually, and the rest of the system or the network. Common applications, HTTP, SMTP, I mean, tons of them. IMAP, POP3, POP. There's lots of applications. FTP, SFTP. You know what I mean? There's a countless number of applications that use the OSI model. Telnet and FTP are given here as examples. Some more mnemonics, if you like it. I think the people do not throw sausage pizza away is a common one that people probably remembered before. The all people seem to need data processing as a top-down, obviously. This is a good diagram for you. Yeah, this is all that stuff that we just talked about is all pretty much summarized here. Here you've got the layers. There's the 7 layers. You've also got DoD model, which is the TCPIP model, kind of mapped here as well. And then the different types of devices and protocols in the middle. That gateway is essentially a firewall, right? A firewall is there's different types of firewalls, but it can operate at all 7 layers. It can actually look into the data stream itself and make packet filtering decisions. Also knowing the structure of the frames packets, TCP, yeah, all that stuff. It should be more segments when you talk about layer 4. Here it just says TCP. That's a protocol. Anyway.
You will need to know how they map, be able to tell, because they'll ask questions between the two.
Segments, packets, frames. Segments, packets, frames. TCP, segments, IP, packets, data link stuff, frames. You have to know that. All right, so TCP. TCP/IP. We like TCP/IP. Actually, 2 protocols, right? TCP is transmission control protocol. IP is internet protocol. Been around since the 70s. It was built by DARPA. This is back when there were a lot of different competing, I think, protocols. Xerox was working on a couple. Anyway, this was the one that sort of won out and became the protocol for the internet. Suite of protocols, UDP, ICMP, and I'll show you a diagram too with all those protocols. TCP and UDP live together at the transport layer. IP and ICMP work at the network layer. ICMP is kind of the traffic cop for IP. IP does all the network, the logical addressing and the routing and all those functions. Yeah, so there's the TCP. There's another mapping. So the application layer, we crunch the application presentation session layers into the application layer for TCP/IP. Transport layer is the same, internet layer, network layer. The network access layer, we essentially take the data link and the physical layer and smush them together. Only 4 layers in TCP/IP. So the network access layer, same stuff that we just talked about with physical, with layer 1 and layer 2, the physical and data link layers in the OSI model are combined in the network access layer for TCP/IP. The same functions take place there, just a different model. Networks include wide area networking, local area networking. These would be more layer 2 functions, you know, if we were to map it directly to the OSI model. When you talk about wide area networking, local area networking, that's where you do, you know, frames, timing on the network happens. Layer 2. Internet layer. Lots of things happen at the internet layer. The internet layer is where IP lives. IP is kind of the king of the internet layer. ICMP is another popular protocol here, which is the Internet Control Message Protocol. It does all the messaging for IP. If a router is getting, you know, inundated with traffic, it'll send a source quench packet. That's an ICMP packet. When you're doing ping, it's an echo and reply. Traceroute at a higher level would use ICMP packets as well. Just manipulating the TTLs, time to live. I'll show you what those packets look like. The two most important ones that you'll need to know functionally would be IP version 4, the IP protocol itself, and ICMP. IGMP lives here too. Anybody know what IGMP is? Internet Group Message Protocol. That would be a multicast protocol. IGMP lives here too, in case you care. IP governs it all. Best path determination, packet switching, all those things occur at the internet layer. The host-to-host transport layer, this is layer up. So we started with the network access layer, the network layer, and now the host-to-host transport layer. The two protocols, really the only two you'll need to memorize are TCP and UDP. Those are the ones that live here. Applications are addressed. So the way IP works with these higher level protocols, in the packet it'll be marked whether it's a TCP or a UDP and what port. The port is usually associated with an application because that'll be used the next layer up to hand it off to the right application. That IP address and port together is called a socket. Yeah, am I making sense? Some of you, this is like really boring because you've been through this so many times, and so you're having trouble staying awake. And the others, I'm maybe going too fast, and so you're like confused and look like you're going to fall asleep. So I'm not sure where I'm at with most of you. But anyway, it's important stuff that you'll need to know for the exam, so maybe it's review. So TCP is the connection-oriented protocol. That's the biggest thing between TCP and UDP. TCP is connection-oriented, UDP is best effort kind of delivery. Actually, UDP is a lot like IP in that it's best effort, it's connectionless. It's like using, the analogy we used to use is it's like using the post office. But I don't get any confirmation whether my package actually got there or not. I don't have a tracking number to track it. It's kind of, you send it and hope it gets there. Whereas like TCP is more like the FedEx or more like the UPS where I get a tracking number. It's tracked in every step along the way and I get a confirmation when that has been delivered. The reason why I'd use TCP's got more overhead, but it is very reliable. UDP's got a lot less overhead, it's connectionless, the packets are much smaller, but UDP would rely on the higher level, the application itself, to do all the packet sequencing and whatever else is necessary, the packet loss. UDP is called a lossy. Also, sometimes you hear it called, it's a lossy protocol. You just assume that you can accept the loss of certain packets in a UDP communication, whereas TCP you wouldn't. TCP full duplex communication, back and forth. There's a SYN ACK back, a three-way handshake for TCP, and then there's a lot of acknowledgments that keep going along the way. I'll show you what the SYN ACK, and ACK back. That's the three-way handshake. It's a SYN packet. It's a request to synchronize, and you'll see in the packet where you can set that flag to synchronize. There's a synchronize acknowledgement that comes back. Again, those two flags are set, and then there's an acknowledgement. Okay, I got your synchronization acknowledgement. Now I'm going to acknowledge that. That's the last packet in the three-way handshake. That's just the ACK packet, or the ACK flag is set. Then you've actually set up a connection. Now we've negotiated how we're going to communicate, and then we set up that duplex, that full duplex communication. That's called a three-way handshake. You don't have that in UDP. UDP is just spit it out there and whatever. Windowing acknowledgement. Windowing is essentially how much data I'm going to accept before I'm going to ask for an acknowledgement and all that kind of stuff, how much buffers play a little bit there. And acknowledgements, retransmission, TCP does all that stuff. You don't see any of that in UDP. UDP, connectionless, no flow control, no windowing, no acknowledgements, no guaranteed delivery, completely unreliable. Just send it and forget it and rely on the application to handle all the rest. All right, and then the application layer, layers 5 through 7 in the OSI model are the application layer. That's the topmost layer in the TCPIP or DoD model. All kinds of applications play here, some that you've heard of before, SSH, Secure Shell, Telnet, FTP. Now, there's a window between the application layer in TCP, where like Telnet is TCP port 23, right, which would be like, hey, send this up to the Telnet application, SSH port 22, yeah. FTP
21.
21, unless we're using, what's that other? Yeah, no, the other form with FTP. No,
GPS?
no, it's old school. I'm trying to think of it. Where we'd have to use 20 and 21. We had a control channel and a data channel. What the hell was that mode called? Anyway, what's that? It's close.
Trivial FTP?
No, TFTP would be UDP port 69. I think 69 or 169. I get it wrong. I don't know where my mind is right now. Yeah, TFTP, Trivial File Transfer Protocol, is a UDP one. Application layer, the process layer, everything. Essentially, oh yeah, I'm still on the application layer. So FTP, HTTP. So knowing these common protocols and what ports they open, if you're a firewall guy, I mean, you would know these. Well, maybe. Now it's not so much like you used to do, where you used to have a lot of command line stuff. Now there's a lot of GUI stuff. But you would know, if you're in information security and you're working at all with technology, it is a good idea to memorize some of the most common ports. Like FTP we said is 21, HTTP port 80, SMTP port 25, TFTP UDP 169. I mean, SNMP is UDP 161. DHCP, I think that's UDP 69. I think I got those two mixed up. But it's good to know kind of those common ports, because you'll see that, you know, when you're doing your own network audits or firewall rule audits or whatever. It's just good kind of basic stuff. That's application layer stuff. This is a good diagram for what protocols, because some of these you've heard of before, like ARP and reverse ARP. We'll talk a little bit more about those two. ARP is Address Resolution Protocol. RARP, Reverse Address Resolution Protocol. Usually you'd use that for a diskless workstation. The way those work is I need to resolve, you know, as it's going down the protocol stack, I need to resolve my IP address, that logical address, to a physical address, right? That MAC address. And the protocol I would use to do that in the TCPIP model would be the Address Resolution Protocol, which is essentially sending out a broadcast saying, hey, who's got this IP address? And whoever on that network has that IP address would respond back, say, I got it, and here's my MAC address. Now, the way you can do an ARP poisoning attack is I can respond that I have that address, and you also respond that you have that address. So now you're going to be responding back to both of us, right? So it's kind of a reflection attack. That's how the traditional ARP poisoning attack works. Reverse ARP works the opposite way. So reverse ARP is I know my MAC address, I have no idea what my IP address is. So I send out, hey, this is my MAC address, anybody know my IP address? And then the system would respond back, say, here's your IP address, assign it your IP address, and then your system would boot up, you know, in a diskless environment. SLARP, I don't even know what SLARP is, I don't know what IARP is, but I'm guessing there's something cool. SLIP, Serial Line Internet Protocol, those are wide area network protocols that you're talking about frames when you're talking about that. Those things will come up, we'll get to those things here, not today, but I think next class. We'll talk about SLIP, we'll talk about layer 2 tunneling protocol, that's the L2TP, PPTP, the point-to-point tunneling protocol. So you know where those live, it's pretty cool. You can see that on the network layer, it's not just IP. Right, there's a lot of IP protocol or network layer protocols like GRE, BGP, RIP. RIP is that routing information protocol I was explaining to you. BGP is Border Gateway Protocol. That's an exterior routing protocol. GRE is an encapsulation. It's a generic routing encapsulation. Anyway, good stuff if you're into networks. It's good to memorize all that stuff. The parts that you will need to remember, ARP and RARP will be covered on the test. They're in scope. IP, ICMP, and maybe, well, IP, ICMP, RIP, BGP. That's probably all that'll be covered on the network layer. I don't think it'll get into EIGRP or IGRP. Those are all routing protocols that are maybe OSPF, but I doubt it. Not deeply
I
anyway.
want to say, and I couldn't find my note, but something with the ICMP, the stuff on the network is like the 4-letter protocols are all basically on the network layer. Because you don't necessarily need to know the RARP and IARP and.
I don't know. You might need to know RARP because
We need to know ARP, but that's a 3-letter.
but RARP is good for the
Yeah.
diskless workstation. But I wouldn't spend any time on CSLIP. I wouldn't spend any time on stun. No time on RSRB. ATMP. I don't even know what ATMP is. But on the network layer, I'd say IP, ICMP, IGMP maybe. They actually have it IMGP. It's actually IGMP. So that's not correct there. Maybe no, you won't need to know MPLS on the net
I think it
you'll need to know TCP and UDP at the transport layer. That's about it there. Session layer.
ESP and AH.
What's that?
ESP and AH covered in previous.
True. Yeah, ESP and AH, encapsulating security payload and authentication header. Those will be examined. Yep, that's what you've got over there. Right, good eye. Who caught that one? Yeah, yep. I didn't even see those on there. Session, DNS kind of plays on both a little bit, but you'll need to know DNS. We're going to cover that tonight. The application layer, FTP, POP3, HTTP, Telnet, SMTP, those will all be there, or testable anyway. SSH, HTTPS, TFTP, yeah. So a lot of the application ones, not SCTP, not COPS, SOCKS. SOCKS will be test, but we'll cover that later. WCCP, I don't even know what that is. RLog and RShell, those are all older, protocols that may or may not be on the test, but you won't have to know the details of those. But this is a good page to memorize.
The question online do we need to know the map the protocols and ports? So basically, yeah, if you see it on this page, you need to know what ports the protocols operate on.
Yeah, certainly the ones that I'll cover tonight.
Yeah.
What port numbers. So encapsulation. So as a packet or as data goes down, data gets added to it, right? And so data at those first 3 layers really there's not much encapsulation that takes place until you get to the transport layer. That's when you start adding, segment stuff and then packet stuff. So the segment stuff would be how to put the data back together again at the other location. You'd see that kind of information in that header. Confirmations, windowing, all that stuff would happen there. At the network layer, where you've got packets, that's where you encapsulate or put another header on, the IP header. And then the IP header is like routing information, messaging information, IP address information would all go there. And then at the frame, you do another encapsulation, which would be preparing it for essentially the physical, ones and zeros. But there'll be mainly logical link control stuff that gets added at that frame layer. But that's all encapsulation as it goes down. When it goes back up the stack, so when the receiving computer gets it, it de-encapsulates. It just strips that off, then hands it back up to the higher level. So segments, packets, frames, and bits. So you'll need to know where segments are, packets are, frames are, and bits are in the model. Bits are layer 1, frames are layer 2, packets are layer 3. Segments are kind of layer 4, and then above, right, if you're talking TCPIP. Those are called protocol data units. The reverse of encapsulation is called demultiplexing. I don't really like that word, because when I think of multiplexing, it's taking multiple signals. And truly, multiplexing is taking multiple signals and preparing them as one. That's a multiplex, and then demultiplex would be tearing it apart. So you can use that word if you want. I just don't apply it so much here. So there's an example. I think maybe I got a better picture here. As it's going down the protocol stack data, then we add a network header Actually, we're adding stuff at the segment level too. Transport, we're breaking the data into segments. The network layer, we're adding that IP header. The data link, we're adding a frame header and a trailer sometimes. Does that make sense? Encapsulation, go down the protocol stack, just you're encapsulating it, and then you de-encapsulate on the way back up. All right, TCPIP protocol suite, included but not limited to IP version 4 and IP version 6 at layer 3. I'm not an IP version 6, expert by any means. Most of the networks, 99% of the networks that we run into are all running IP version 4. The only time you run into IP version 6 is sometimes in that auto negotiate. We like to turn up. There's two schools of thought with the IP version 6 auto negotiation. I subscribe to the theory that if I'm not using IP version 6, I turn it off. But I've heard some consultants say to leave it on. I don't know. I turn it off because I don't like auto negotiation. I don't like things on my network that are doing things I don't understand what they're doing, right? And so when I leave IP version 6 on, it will auto negotiate and automatically start communicating with other systems that speak IP version 6 on that local network. And I'll talk a little bit about that later too.
Point-to-point communication is more efficient over IP6.
But if I'm not using it, yeah, that's the part that I don't like. I mean, if I were using it and had it configured, then I'd like it, maybe. TCP and UDP live at layer 4. Lots of protocols at layer 5 through 6. We've talked about, a lot of those already. IP does fit strictly in the internet layer. There's no crossover with IP. ARP and those others actually span ports. MAC addresses. Now, we can set MAC addresses in software. Now, back in the day when you couldn't do that, hardware addresses were hardware addresses. They were burned in at the factory, right? It was called the OUI. Do I even have it up here? Yeah, the Organizationally Unique Identifier. I could never remember what OUI stood for. I just knew that every system had an OUI. Half of the OUI was assigned to the manufacturer. The other half of the OUI was assigned by the manufacturer, right? So the IEEE would handle these registrations. So it would be really easy to tell on a network what type of device was on my network based on its MAC address, right? If the MAC address was, the first half of the OUI was or the MAC address, which is the OUI, was assigned to Cisco, I knew it was a Cisco system, or I knew it was a 3Com system, or whatever. Nowadays, you don't really use it like that anymore because you can change it in software now. You used to be able to do that. But anyway, MAC addresses are also referred to as a hardware address, burned in at the factory in the traditional sense. They can also be changed in software. MAC addresses on a local area network do need to be unique unless you're doing something like an ARP poisoning attack where, there's nothing, the network doesn't stop working if two systems have the same MAC address. The two systems that have the same MAC address will just communicate to others like they're the same. You know what I mean? I suppose switches could get a little pissed off too. The way switches work is they build a MAC address table. Either they learn one or you configure one. And say there's 30 systems connected to or 32 systems connected to my switch. The switch will learn the MAC addresses of each system that's connected to that switch, and it'll only forward traffic that goes to the port that it belongs to, right? So, I'm just going to simplify, say a MAC address of 1, because I don't want to go through the whole, all the hex. But a MAC address of 1 is on port 1. Rather than broadcast, if there's something that comes in port 3 for MAC address 1, rather than sending it out to all ports, the switch will only send it out to port 1 because that's where MAC address 1 lives. Does that make sense? Whereas a hub would send it all to all of them. That's essentially the collision domain also. Collision domains on switches are limited to the switch port. All right. Historically, MAC address is 48 bits long. The first half of the MAC address was the OUI, the 24 bits, which was assigned by the IEEE to somebody. You can get a list of the OUIs, but I don't know who's really maintaining that anymore. It's more for historical purposes. There's a MAC address, an IP config / all on a Windows system. You would see the MAC address there as well. That's hex, if you don't know what hex looks like. IEEE, created by EUI, whatever, 64-bit MAC addresses. I don't know really the purpose of this other than the fact that you're running out of MAC addresses if you're burning in MAC addresses as a manufacturer. Because the OUI is still the first 24 bits. So 2 to the 24 tells you what the address space is for the OUI, so 2 times 2, 24 times. That's how many OUIs you could potentially have. In most cases, a manufacturer has multiple OUIs assigned to them. MAC address. IP version 4 sometimes is referred to as IP. 70s ARPANET, we've beat that horse now. Not that I'm into beating horses. Well, because you never know, man. I mean, people are like so politically correct now, and people get offended by all that stuff. That's an old saying that's used to use. You can Google it. I didn't make it up. I don't beat horses. For the record. This is probably being recorded too.
I think it's only dead horses.
Yeah, it's like.
Oh, so you can beat dead ones. Oh, so I do beat dead horses.
No,
Don't beat
I
dead horses.
don't want to beat a dead horse.
You don't want. I am beating a dead horse. I am beating a dead horse right now.
Yeah.
I don't know if I want to talk to you anymore. All right, the helper protocol for IP is ICMP, Internet Control Message Protocol. Unreliable, best effort delivery. ICMP is the one that kind of watches things for IP and sends messages back and forth when things aren't working right. 32-bit IP address, so they call it dotted quad. Who calls it dotted quad? What do you typically call an IP address? No, when you break it down into its 4 octets.
Mm-hmm.
Yeah, I refer to it as octets more often. So when I saw the dotted quad in the book, I was like, you never called it that. But an IP address, so 32 bits, each one of those is an octet. So the 192.168.2.4, those are in binary 8 bits, right? So do you remember the 128.64.32, 16.8.4.2.1? So you can tell what bit number is on. So in the 2, it's the second bit from the right. In the 4, it's the third bit from the right, right? So if you get into IP addressing, it's kind of fun because that's what you would do if you were subnetting networks and getting into all that stuff. But essentially, it's 32 bits long, and you'll see when I show you the header, it's 32 bits long. It's just segmented for us to read it. You know, human beings, we just break it into 4 octets. Yeah. So 2 to the 32, we ran out of IP addresses, or we thought we were going to run out of IP addresses before we did some funky things with NAT and private IP addressing. But that's the address space. The total address space is 2 to the 32, which gives you 4.3 billion addresses. There's an estimated, on the internet today, I think there's an estimated 7 billion systems on the internet today. So that's assuming, there's got to be somewhere's got to be a lot of doubling up going on, or a lot of people are using IP version 6. They've already moved to that. Because that's a 128-bit address. So 2 to the 128 is like some huge number. How many?
39.
39 what?
I think it's 39 numbers long.
It's big. Yeah, I don't even know what to call that. But but that was one of the primary reasons for going to IP version 6 was that we were running out of IP address space in IP version 4. A secondary purpose was IP version 4 has no security built into it. Everything's, it's not a secure protocol. So IP version 6 took IP, the same concepts, and built security into it. So IPsec is part of IP version 6. It's an add-on to IP version 4. Key fields in the header. I don't know how deeply you'll be tested on this. Maybe some of this is FYI, but I think in general, knowing these things is helpful. This is what the header looks like. But what you'll see in the header is the IP version, the length of the IP header. You'll see the IP address in there. You'll see what protocol do I hand this off to next is in the header. This is what the header looks like. Version, header length, type of service, total length of the packet, identification, fragment, offset. That fragment offset isn't used all that much in IP because it relies on ICMP to put packets back together again, or the upper level protocol. TTL, every hop that an IP packet hits will decrement that TTL by 1. That's so the packets don't live on the network forever. When it gets to a 0, it kills the packet and probably sends an ICMP message back. The protocol that it belongs to, IP or otherwise. Header checksum, there's a source and destination IP addresses. You can see that that's 32 bits across. If you're looking at the scale, there's 4 bytes there, 4 bytes, 32 bits across, and you can see the source and destination IP addresses are there. And then just options that are used. Now the flags that you could set in each one of these is down at the bottom. It's good for information, good for reference if you need it. It's good stuff. IP fragmentation. So sometimes, one system might send data that's too large for a network before it segments it. That's called the maximum transmission unit, usually the MTU. The MTU typically is 1,500 bytes. If it exceeds that, then you have to fragment in a switch or router. Unless the do not fragment bit is set in the header, which means you cannot fragment this, then what you'll get back is an ICMP message saying, we dropped the packet, couldn't deliver. But fragmentation allows different networks using different MTUs or maximum transmission units to fragment and then reassemble packets at the other side. IP version 6, there's the number. Undecillion? Sextillion? I think sextillion is easier than undecillion. 2 to the 128th, that's a lot of addresses. So theoretically, each one of us could have, I don't know, probably a few thousand IP addresses assigned to every human being and every thing that we have. So the theory is really good. What's slowed adoption is just like chip and pin on credit cards. Like we just don't do things unless we sort of are forced to. So someday, maybe we'll move to IP version 6 more widespread, but it's been around for quite a while now. Simpler routing, simple address assignment. It's more difficult for me to read because what they did with IP version 6 is they started collapsing numbers where there's repeating numbers. You can collapse and put the colon. Well, that just confuses the crap out of me. So
you gotta go and figure out how many it's missing. And
yeah. So when I look at an IP version 6 address, yeah, I have to refer to my friend Google to figure out what the hell this is doing. But anyway, that's why we went with IP version 6. The header is larger and simpler than IP version 4. Look at how simple it is. Right? Very simple. The source and destination now are 128 bits, but everything else is really simplified. These are the fields that you have, the IP version 6, traffic class, flow label if you're doing quality of service, sometimes with voice or critical network traffic. Payload length, yeah, hop limit. Everything that goes on a network should have a hop limit or a TTL associated with it, otherwise it just sits on the network forever until something just trashes it. There's the header. I don't think you have to memorize anything here other than knowing that it's a 128-bit address and that it's simpler than an IP version 4 IP header. Auto configuration. This is one of the benefits for some people for IP version 6. It's scary to others, is this auto configuration. So there's stateless auto configuration and stateful. Stateful is if I'm using a DHCP server to assign IP addresses. Stateless is it just assigns it itself. The system, and it'll use its own MAC address and other things to create its own network address to talk on the network. Now these packets won't route; they're link local addresses, which means that they'll stay on their local network. So keeps it from just kind of expanding to everywhere. Because the last thing I'd really, really want is a system on my network that auto configures itself that can route out to the internet. That could be a problem. Yeah. So you understand the difference here between stateless and stateful? Stateful, you're using DHCP or something like that to configure the IP addresses, and stateless is it just does it by itself. An IF config or an IP config, if you're on Windows, gives you these types of things. You'll just have to memorize this. I really am not an IP version 6 expert by any means. Scope global, scope link, or link local. I think you'll just have to read IP version 6 stuff. And if you're not using IP version 6, you'll probably just be like me and forget it pretty quickly. How many who?
How many zeros is scary?
2? 2? Yeah. Yeah. I can read this just as well as you guys can. I mean, I would just suggest you guys read IP version 6. I'm not an IP version 6 guy at all. Sorry. I suppose I could have read up on IP version 6, but then I'd have to discard that as soon as I'm done with the class because I just don't use it. This is a stateless configuration. It's global address. Good reference. Here's some IP version 6 security challenges. Like I was saying, I don't like auto negotiation. I don't like auto configuration of anything on the network if I can help it. That can become an issue because there could be, if I'm using, like all my systems are set to log and alert on IP version 4 traffic. And I've got systems that are communicating in IP version 6 traffic. That's a covert channel that I don't know exists. I could know it exists. I could be doing, you know, intrusion detection and prevention would pick that stuff up. But if it's on links that I'm not monitoring, most people don't run IDS, IPS on local area networks, you know, behind firewalls and DMZs. So there could be all kinds of communications that I just never see if I allow IP version 6 to run on the network. So that's the main reason why I don't like IP version 6. The third bullet point certainly applies to me as well. I have limited experience with IP version 6, so oftentimes I won't know what I'm looking at. That's the same with a lot of our customers. They'll see things, they'll do packet captures, and try to decipher what it is that they're seeing, and they can't understand it because it's IP version 6. Yeah, so those are some of the security challenges of why I steer away from IP version 6 if I can help it. If I were forced, if like, you know, a lot of our customers were using IP version 6, well, then I'd be forced to learn it and master it, but still most are using IP version 4. All right, so in IP version 4, we've got these concepts of classful networks and classless networks. Classful networks are ones that Brad would run. Classless networks are ones that I would run, right? Because I don't have any class. Brad does. That's a security humor.
I appreciate you being that generous.
Oh, wait, crap, I said that wrong. Classless.
Oh, that's more accurate.
Yeah. So classful networks are just broken down by certain organization or organizational units or whatever. So there's really only 4 classes that are used in practice. E is experimental, but A, B, C, and D. And we'll go through what those classes are. This is a good one to memorize if you don't know classful networks for IP addressing. The leading bits are always a good tell for what type of IP address this is, what class. So all class A's will all be zeros, right? They'll all start with a 0 for the leading bit. That means I've got 64, 32, 16, 8, 4, 2, 1, right? The 128 bit is off. So it's going to be a 127 or lower, right, for that class A. Does that make sense? A 10 would be the 128 bit is on, the second bit, the 64, is off, and all the rest are on. So it's going to start with a 192. I'm sorry. It's going to be below a 192. A class C is 11. That's going to start 192 and higher. Does that make sense? Number of networks. Now, you get this. If you really want to know number of networks and number of hosts, do you know I'll teach you a little bit about subnetting, but you know the equation 2 to the x minus 2? You ever heard of that before? Do you guys want to know subnetting? We got time. Okay, So 2 to the x minus 2. So in an IP address, there's a subnet mask that's applied. The subnet mask delineates what portion of this IP address belongs to the network, and what portion of this IP address belongs to the host, right? So where that subnet mask falls in the 32 bits of an IP address, so let's say my subnet mask is 255.255.255.0. 24 bits are assigned to the network, and how many bits is that? 8 bits are assigned to hosts, right? So how many hosts could I run on that network? 2 to the x minus 2. 2 to the 8th minus 2. So 2 to the 8th is 256 minus 2, 254 hosts. Right? How many potential networks could I have if I've got 24 bits assigned to networks? 2 to the 24 minus 2, that's how many potential networks I could have with that 255 subnet mask. Does that make sense? If I take like a 255.255.0.0, that's a class B. 16 bits are for the host, 16 bits are for the network. So 2 to the x minus 2, 2 to the 16th minus 2 gives me how many? 16,300 something, 84 hosts, something like that. That's how many hosts I can run on a class B network. 2 to the x minus 2. 16,000 what? 64,000? I don't know. Yeah. You'd have to do the 2 to the x minus 2, just do the 2s. But that's how you come up with these numbers. Now, if I wanted to subnet a class B where I've got a 255 or a /16 CIDR format, we're going to get into CIDR format. That's the classless interdomain routing format. The /16 just means 16 bits are assigned to the network. The rest is assigned to the host. But let's take, I take a class B, I've been assigned a class B, but I only need 600 systems on this network. It wouldn't make sense for me to put 600 systems on a full class B because I'm wasting an entire 65,000 IP address space, right? So how many bits would I need to assign to the host portion? So how many hosts did I say? 600. So 2 to the x minus 2 equals 600. So 2 to the x equals 602. Figure out what the x is, and I'll tell you how many bits you need to assign to the host. And that's where you would subnet that class B network. Does that make sense?
There's some good comments. Subnetting is the reason I went to IPv6.
Oh, so somebody is an IP version 6 expert. Awesome. I like IP version 4 because you really do get a lot of control. You can do a lot of traffic shaping with IP version 4. You can create networks that are spaced for your purpose, right? But subnetting, and I can explain it more on a whiteboard, but that's where the 2 to the x minus 2 comes from, and that's where a lot of these numbers come from, right? How many bits are assigned? Because a bit can only be on or off, right? That's the 2 to the x, how many bits? Yeah. Hopefully I'm making sense. So starting addresses, ending addresses, all that stuff. So a 255 in an octet is every bit is on. Right? The 128 bit is on. I'm sorry, the 128 bit is on, the 64 bit, the 32, the 16, the 8, the 4, the 2, the 1. That's how those are numbered, you know, when you're. I don't know how much that you really need to know for the exam, but it's really cool. And it's really important to know if you're running an IP version 4 network and you're the network architect, you want to space stuff right and all that stuff. So here's the classless interdomain routing. We refer to it as CIDR. So you had the classful networks. That was this. Class A, Class B, Class C, Class D, which is for multi-class. Class E is reserved. Nobody uses Class E. It's experimental. I suppose somebody does, but we don't. The ones that are used in production where we actually set IP addresses and networks is usually A, B, or C. You can see the address space for an A is 16 million IP addresses. So and you see this a lot. We go to networks all the time where people have assigned like a 10 dot whatever network, and they've got like 60 computers, right? It's overspaced, which is okay. I mean, it's not like a huge deal. But it's excessive. Class B splits it down the middle. Class C is really the last 8 bits. The last octet is reserved for hosts. Yeah, so 0, 128, 192. You should be able to tell the class of the IP address space pretty quickly. Classless interdomain routing allows us to do this subnetting, allows us to make networks more shaped for, you know, their intended purposes. Is the RFC in here? 19. No, we don't have the RFC in here. But anyway, that's also where you see the CIDR notation, is where you see the slash. That's how many bits are assigned to the network. So if you look at the 10.0.0.8, 8 bits are network, the other 24 bits are host. See a 192.1.2. You can use them on classful boundaries. So you could use like a class C would be a /24, class B would be a /16, a class A would be a /8. Those are classful boundaries with classless interdomain routing. But that doesn't mean that I can't do a /12. Doesn't mean I can't do a /22. That's the classless interdomain routing. Does that sort of make sense? Now, if you don't do subnetting and you never do subnetting, you probably don't care. But knowing the difference between classful and classless IP addressing will be important for the test. RFC 1918 addressing. This is, you'll need to know RFC 1918. So when everybody had a public IP address, or when IANA is the Internet Assigned Numbers Authority. They're the ones who assign public IP addresses. I think they also assign autonomous numbers, ANs, which is used for exterior routing on the internet. The way it used to be was everybody would just assign IP addresses whatever the heck they wanted to. That led to the exhaustion of IP addresses much quicker than we wanted to. So then we came up, or the world came up with RFC 1918, which named these are non-routable private IP addresses. When I say non-routable, they're routable but not routable on the public internet, right? So you'll never, if you try to ping, route something in a 192 address space on the internet, the first router that gets it is going to drop it, or the first firewall that gets it, it's going to drop it, because those aren't routable on the internet. These are private IP address spaces. So the 10 network /8 is a private IP address that's never routed on the internet. 172.1.6/12. So it's not on that /16, that classful boundary. It's a /12. And the 192.168/16 are the RFC 1918 private IP addresses that are not routable on the internet. You'll need to know that. Network address translation. So being that I name everything in my boundary, so the perimeter is usually it's got a firewall or a router or something there. Everything behind that I own is private IP addressing. Everything on the internet is public IP addressing. There needed to be a translation between this private and this public. Otherwise, we were never going to communicate. That's where network address translation takes place. That's part of the same RFC. RFC is requests for comments. They're public documents. They're standards for the internet. Lots and lots of RFCs. Everybody ever read an RFC before? Pretty exciting read, huh? It's all just plain old text. A lot of it. So there's 3 types of network addressing. There's static, pool, and then what we call port address translation. Static is a one-to-one. A pool is many to a few. So I'd have a pool of public IP addresses and a lot of internal private IP addresses. So I would be able to communicate, and as I communicate, I would be assigned by the router or the switch, or it'd be the router or the firewall. I'd be assigned one of these public IP addresses, and then the router or the firewall would keep a table of which private one did I assign to which public one, so that it can perform that translation back and forth. Static NAT is a one-to-one. You don't see a lot of static NAT. You see the most common one you see is port address translation. And the reason why it's port address translation is because it's one IP address that's going to be shared by multiple internal private IP addresses And the way we do the translation, or the table that's maintained by the router of the firewall, is by port number, right? Because in every communication, there's a source port and a destination port. So I would just, okay, I assigned this IP address and this new source port to this private IP address, right? So conceivably, I could use one, and there's other strategies, but I could use one IP address for one public IP address for up to 65,000 some number private IP addresses, right? And that would be all port address translation. It just maintains a table. Does that make sense?
Go one over that, and one half.
You'd have to have another private IP address.
You get a second IP address.
It automatically assigns
It would very rarely happen. You'd have to have 65,536 simultaneous communications going on the internet. And chances are very good that you wouldn't have that all in one site going through one gateway, one firewall. You'd have multiple locations where they'd have their own public IP too. So I've never seen anybody exhaust a port address translation before. I don't know what would happen. I assume the communication would just drop, or it'd recycle, potentially. I suppose actually, maybe we have done it. You ever shut down your firewall before at home? Playing around with stuff? Doing a bunch of...
I've never done that at work, accidentally closing.
Yeah, done a bunch of like port scanning or something, and your firewall just pukes because I think that port address translation table just gets filled up and doesn't know what to do with it. Maybe that's what happens. It stops communication. I don't know. Here's a diagram. This is also from the book. A static is the one-to-one. The pool is the many to few, and the port address translation is the many to one. Here's ARP and RARP. ARP is Address Resolution Protocol. Its purpose is to resolve an IP address or a logical address to a physical MAC address. That's the purpose of ARP. So layer 2 MAC addresses and layer 3 IP addresses. Again, layer 3, logical, layer 2, physical. Resolves IP to MAC address, and it's just an ARP broadcast. You know, who's got this IP address, and whoever's got that IP, and that's a broadcast. Whoever's got that IP address will respond back, hey, I've got that address, here's my MAC address, and then you start your communication. Computers communicate in TCPIP, they communicate by, on the local network, they communicate by hardware addresses. Pretty simple. Reverse is just the other way around. I know my MAC address, but I don't know what my IP address is. You'd see this in like a diskless workstation. Who's got, you know, who has MAC address blank, tell whatever, and then whatever, and then assign the RARP server will assign the IP address. Other types of communication on a network: unicast, multicast, and broadcast. Unicast, one-to-one, multicast, one-to-many, broadcast, one-to-all. That's how those communications work. All those are acceptable on certainly on a TCP/IP network. Broadcast traffic is sent to all the stations on up to layer 3. Layer 3 devices break broadcast domains. So you know, VLANs, you know, broadcasts typically don't transverse VLANs. You can set your router to do that, but you know, why? So broadcast traffic is sent to all systems on a LAN until it runs into a layer 3 device. Two types of broadcast addresses: limited broadcast, which is essentially just, you know, all bits are on. It just goes everywhere. The other one is the directed broadcast. This is how you could configure your router to forward directed broadcasts, but most routers won't do that out of the box. So, and I don't know why you would set up directed broadcast, but this would be like, if I'm on this local area network and you're on that local area network, I want to broadcast on your local area network, not on my own. The 255 would be a broadcast on my own local area network. A directed broadcast would be a broadcast on another over a layer 3 device. Rare, usually, right? You could do the local directed broadcast on your own network too, I suppose. Just take a segment of your own traffic, but I don't know how that would work. Layer 2 broadcast reaches all the nodes in a broadcast domain. That's from the book. It's actually a collision domain. Layer 2 is breaks down collision domains. Layer 3 breaks down broadcast domains. So a switch itself is a broadcast domain, but each port is a collision domain. Does that make sense? Okay. Ethernet broadcast, MAC address, all Fs, all bits are on. Those are broadcasts. Yeah. Promiscuous mode. Did you just giggle at promiscuous? No, not that kind of promiscuous. Sort of. Promiscuous, we would use this for sniffers, packet sniffers, typically run in promiscuous mode. They'll just process, they're configured to process whatever comes on the wire, right? Normally, my computer will only respond to traffic that's directed to it, right? If it's connected to a switch, it's only going to see traffic that comes down that switch port that's directed to it. I can set my adapter into promiscuous mode, which would process everything that it sees on the network. Now, if I'm on a switch port, I'm still only going to see the stuff that comes down that switch port, right? I'm not going to see all the network traffic. That's where we put like a hub or well, it'd be a hub. We would put a repeater there, or a span port. If you've ever heard of a span port on a switch, which would take all the traffic from this port and put it down my port as well as the stuff that comes down my port. But promiscuous mode, because one of the things you get for people who don't understand how promiscuous mode works or broadcast domains is they wonder why, when they're sniffing network traffic, they're not seeing the traffic that they want to see, or that they're hoping to see. It's because they're connected to a switch, right? You're only going to see the stuff. The switch is going to break down that broadcast domain and only send traffic destined for that MAC address, right? And MAC address broadcast. So you'll also see all. If you do a promiscuous mode on a switch, you'll also see all the ARP broadcasts because those are ARP broadcasts, but you won't see much above, beyond that. So promiscuous mode, all unicast traffic on a network segment, and truly unicast if you're on a switch port, but if you're on a hub, you'll see all traffic. All traffic that goes on the wire, you'll see it. Network intrusion detection systems, some of them run in promiscuous mode. Normally they only see the traffic sent to them. Mentioned all that stuff. Yeah. Any questions on promiscuous mode? Not your style, but this style of promiscuous mode? All right, TCP, reliable, layer 4. We're beating this into you if you don't know it already. Three-way handshake. This is the SYN, SYNAC, and ACBAC. Those are the three packets in a TCP. All TCP communications do the three-way handshake. Every session with the TCP protocol does a three-way handshake. You can see where they live. TCP, UDP, again, would beat that pretty good. TCP is connection-oriented. Retransmission, windowing, all that stuff happens with TCP. Key TCP header fields. The header field is 20 bytes long. You don't necessarily have to memorize that it's 20 bytes long. It's more kind of for FYI. Fields include source and destination port. That's really important. I don't know if we get into here, if we talk about ephemeral ports and ports that are assigned. Ephemeral ports are typically those ports over 1024. So the ports that you've seen, that we've talked about so far, SMTP, FTP, HTTP, those are all lower than 1024. Those are assigned ports. IANA assigns those ports. Typically, you register those. Not to say that I couldn't get HTTP to run on port 38 or port, 8000. You could do that. But it's normally assigned ports are those ones below 1024. All those ports above 1024 are called ephemeral ports. Those are freely used by kind of whoever. There are some that are assigned or just generally well known, but in general, they're ephemeral ports. When my computer wants to communicate on the network, what normally happens, if I haven't monkeyed with things, is it will choose one of the ephemeral ports to be my source port. Right? And then whatever I'm communicating with on the other side, depending on what application, will be an assigned destination port. Right? That's so that when it comes back to me and I need to I know where to hand it back up to what application made that call. Does that make sense? Source ports and destination ports. So when I'm communicating, I'll assign a source port based on one of those ephemeral ports, and then the response back. Anyway, so that's source and destination. Sequence, acknowledgement numbers, those things are all assigned and negotiated. Full duplex communication flags. This is the flags SYN, SYN-ACK, or SYN, ACK, FIN, urge. There's a lot of different flags for TCP. Just basically what this flag is intended to do, and then that window size, how much data before I want an acknowledgement. This is what the packet looks like. Source port, destination port, sequence number, so we can put the data back together again. An acknowledgement number. If I'm expecting this acknowledgement, I don't get this acknowledgement, I'm going to send a retransmission request. Offsets, putting packets back together again. You can see the different flags. The ones that are the most common, urgent, acknowledgement, push, not so much, reset, SYN and FIN. When we're done communicating, we'll send FIN flag, or send a packet with that FIN flag set. Checksums, pointers, all that kind of stuff. I've already talked about TCP ports, so that 51178 would be an ephemeral port. And now normally when you see this stuff on the network, even if normally that would be a source port, right? Unless there's some application running on that. So I mean, just if I saw it, I didn't even pick out source and destination, I would know that that's probably a source port. You would see it in the packet capture anyway. The port field 16 bits long, so it can be 0 to 65, 535. Reserved is 1023 or lower. Ephemeral ports are that 1024 and higher. Lots of well-known ports, obviously HTTP port 80, HTTPS port 443, SMTP 25, all that kind of stuff. If you want to know a list of well-known assigned port numbers, there's IANA, Internet Assigned Numbering Authority, who handles that. Yeah, all that stuff. In Linux systems, Etsy services is where you'd find well-known ports. So socket pairs. A socket pair is an IP address paired with source, and this is on both sides. So this is a netstat output. You guys all have done netstat, all you network people, but for you who haven't done network people, go open up your computer and type, open a command prompt and just type in netstat. You can learn the flags later in the settings, but just type netstat and you'll see stuff like this. This is the protocol that's being used, the source IP address, the source port, the destination IP address, the destination port, and the status, of the communication. Source port, source IP, source port, destination IP, those together are called a socket. Or, socket pair, whatever. This is what TCP, we've already looked at this. These are the flags and what they mean. Urgent. Now, acknowledgement, the three-way handshake. So the SYN flag would be set in the first packet. I would have an ephemeral port, probably assigned as the source port, and whatever I want to communicate with on the other side as the destination port. And it's just a request to synchronize, or a request to communicate. What you'll receive back is a SYN acknowledgement. So the SYN flag is set, the acknowledgement flag is set, which is, yeah, I'm ready to communicate. Let's get it on. And the packet back then would be the synchronized packet, another acknowledgement that, okay, I'm ready. And there's also other things that are set in those, including window size and other stuff, but those are the most common ones. When you're done with the communication, the FIN packets, I don't know how many people really code, FIN packets. Normally they just leave open these half connections. It's frustrating. So that's another way. So you talk about port scans. Right? A TCP port scan, there's different types of port scans that I can run. I can run a Christmas tree port scan, which is all flags on. Right? Different systems will react differently with all the flags on. Some will just discard the packet, some will reply back something weird. I can set different types of combinations of flags in different systems. We use those for fingerprinting when you're doing penetration testing. Set all kinds of different flags to all kinds of different options and see what you get back. Nmap, you guys ever use Nmap? Nmap's a classic tool for doing port scanning. You can do all kinds of cool stuff with that. 2 new flags added in 2001. I don't know how important those are. for the test. The TCP handshake, this is the TCP handshake, different types of port scans you can do. Yeah, you can just do a port scan with a SYN flag, that'd be a half open connection. You used to be able to flood buffers by sending a bunch of SYN packets consecutively, because what would happen is the computer that was responding would send the SYN ACK packets back and then hold that buffer space open, waiting for you to send that last acknowledgement, right? And if you sent enough packets in a short enough period of time, you could crash the system because it kept holding all these things open and then crash the buffer and it wouldn't communicate anymore, right? You used to be able to do that in the MT days. It's one of those types of attacks. But anyway, SYN, ACK, and ACK-back, that's your three-way handshake. And where the other flags are used, reset, fin, purge, whatever. Here's an example of SYN, ACK, and ACK-back. Any questions on the three-way handshake? No? Pretty basic. UDP. You see how, there's not much to a UDP header. Source address, source, destination port. There's no, checksum is rarely used, but there's no flags, there's no synchronization, there's no windowing, there's no negotiation, there's no fragment offset, there's none of that stuff with UDP. Simple, faster, TDP, for TCP, no handshake, no session, no reliability, send and pray, like using the post office, right? Just send it and hope it gets there. Simplex, shorter, fields are easy, operates at layer 4. It's TCP's friend, sort of. There's that lossy, I use that word lossy. UDP is a lossy protocol. The reason, if I was coding something, one of the reasons why I might choose UDP is you have either built all the connection-oriented stuff, session stuff into the application, or I just don't care about packet loss. But a lot of times you don't really care about packet loss in like audio files, like audio streaming. So audio streaming sometimes we'll use UDP because we normally don't pick up, audibly individual lost packets unless it's, a lot of them spaced together. But, those are lossy kind of things. Video streaming sometimes is lossy. We can accept it. That's all we're going to cover about UDP.
Did you tell the UDP joke earlier? I wasn't paying attention.
What UDP joke?
I'd tell you, but you might not get it.
Ah!
Come on!
Humor.
Come on! Any more than that.
I get it. I like it. You get some of this. You know what I'm saying? You would, but you laughed at the promiscuous.
It just sounds like a really weird, Sears Club or something.
Promiscuous mode?
Promiscuous network.
You could probably get 2 network adapters to get it on.
Yeah.
Never tried it. So ICMP, this is kind of the traffic cop and the messaging piece for IP, right? This plays with the network layer. Helper protocol, they call it. In ICMP there are in the network layer, there are multiple protocols that live there, but there's no sense of ports here. There's protocol numbers, like GRE is protocol number 47 in the network layer, right? And the reason why I remember that is because PPTP was really reliant on GRE back in the day when you'd use PPTP for VPNs. Does anybody use PPTP, Microsoft VPNs anymore? Still? No. But that's why I remember that. But protocol numbers are used at the network layer, not port numbers. ICMP has no concept of ports. The most common, ICMP types are the ping, where I send the echo and the reply. Same, same concept as, ping for like submarines and such. This is an ICMP packet header. Packet header, correct. Basic. Type code checksum, and then whatever message information I want to include. Now you can see the different types. So type 0, echo reply. Type 2, destination unreachable. There's source quench. There's all kinds of different messages that can be, attached to an ICMP packet. Routing devices are the most common devices that, for ICMP packets, for a number of things. Ping, same thing, same concept as the sonar, echo request, echo reply. Ping's good for troubleshooting, but a lot of people block pings now, at least externally, but we would use it for mapping networks and tests and penetration tests along with port scanning and other things. So that's why we typically block ICMP at the borders of networks, and even ISPs sometimes do that. Attackers use ICMP to map target networks, find out what's alive, what's not, figure out where we're going to attack. Now, there's a lot of things you can do to masquerade, pings too, right? You can, anyway, throw attackers off and get deceptive, but probably not into that. Unanswered ping, so traceroute. Traceroute also uses ICMP packets. The way traceroutes work is we just set the TTL, the first one, to 1, right? So then the first router that gets it is going to decrement that TTL in the ICMP packet to 0, and then send a destination unreachable reply back to the source. And then I'll send another one with a TTL of 2, so it goes to that router, gets decremented by 1, goes to the next router, gets decremented by 1, and then you get a destination unreachable coming back. So now I know the second hop, right? And then I set it to a TTL of 3. That's how a traceroute works, but it all uses TCP packets. You can use in Unix and Cisco systems, you can use UDP packets for the same function if you wanted to. But the whole point is you just increment the TTL for the number of hops, and that's how you get those replies back on, the route to get to a destination, which again is real. It's helpful for troubleshooting, but it's also helpful for attackers because you can start to map networks, right? If I don't know the full IP address range for the target network, I'll just continue to use IP addresses and wait for that route to change to another location. Right? And then I can probably assume that that's a boundary for the network. Yeah. There's a diagram just explains what I just told you. So the first one would be TTL 1, the router decremented to a TTL of 0, which then it's a dead packet, time exceeded. So then I send another packet with the same destination IP address with a TTL of 2, makes it through the first router. Now the TTL is 1, the second router decrements it to 0, time exceeded, or so on and so forth. Usually up to about 15 packets, but you can exceed that too. 15 is usually the limit for TTLs. Routers, if you exceed that in some routers, they'll just drop the packet because it's malformed. Application layer TCPIP protocols and concepts. Here's some of the application stuff. We have already talked about it numerous times now. The TCPIP's application layer maps to the session transport and presentation session and application layers of the OSI model. These protocols have a lot more functionality to them. Usually there's a human interface to a lot of these applications. So Telnet, what do we not like about Telnet? Plain text, right? Usernames, passwords are spent in plain text, and so is the data. But Telnet was, it's somewhat legacy now. A lot of people have moved. Well, I shouldn't say that. A lot of people are still running Telnet. TCPIP port 23. We don't like Telnet. An alternative to Telnet would be SSH. Telnet is short for terminal emulation. This would be sometimes people say, get a command prompt or a command line. Same kind of stuff. BTY terminal emulation stuff. Secure Shell is a better alternative. Secure Shell runs on port 2222. I was going to say 222. That's not even right. Port 22. FTP, file transfer protocol, also clear text. So FTP, sending confidential information, including usernames and passwords, are sent in clear text with FTP. FTP port is port 21. Active FTP. That is what you said, isn't it? Oh man, I'm sorry about that. Active FTP is where you use port 20 for command and 21 for traffic. 21, or today's FTP is all running over TCP port 21. But you used to have to open port 20 also. So it's FTP, yeah. Not only do we not like FTP because of all the clear text stuff, but a lot of people haven't set up FTP correctly, so there's a lot of anonymous FTP out there, so you don't even have to authenticate to see stuff. You can find a lot of confidential information on anonymous FTP servers around. If you want to find all the anonymous FTP servers, you choose something like Shodan. Maybe you ever use Shodan? Yeah, great place to find all kinds of cool targets. What else about FTP? I think that's it. Oh, Secure FTP, which is it's part of the same suite as SSH and Secure Copy, SCP. All use port 22, so you can do the same file transfer stuff on port 22, depending on which application, right? So Secure Shell would be, runs over port 22, but it'd be a terminal emulation function of the same application. Does that make sense? Secure Copy would be the alternative to FTP, the one we like better. Trivial File Transfer Protocol, UDP port 69, so connectionless. Lossy, we would require the application to do it. The place where I used to use TFTP the most often would be saving off, configs from routers and switches and stuff. You'd use TFTP for that. No authentication, no directory structure. It truly is sort of dumb. Now, you can have TFTP clients that can have that built in, but the protocol itself doesn't have any of that at all. SSH, Secure Shell, this is a replacement. It's part of the whole family of Secure Shell, Secure Copy, and what's the other one I'm missing? I can't remember. But anyway, it's the same function as Telnet, but it's encrypted, including usernames and passwords. You've also got extensions where you can use certificate-based authentication and all kinds of other stuff with Secure Shell. Secure FTP, oh, that's the one I was thinking. Secure Copy and Secure Shell are all essentially the same application. TCP port 22, that's all we need to know about SSH. SMTP POP and IMAP, SMTP port 25, POP 110 and IMAP 143, these are all mail, store and forward type protocols. SMTP, simple mail transfer, that's between servers. SMTP is typically between two servers. POP and IMAP would be from clients to servers. POP3, post office protocol, all that kind of good stuff. 110 and 143 is what you need to remember about SMTP, POP, and IMAP. DNS, so DNS, domain name system, uses two ports, UDP and TCP, UDP 53, TCP 53. The way most traditionally it works is UDP queries are made on, DNS queries, which is for name resolution. It's to resolve a name to an IP address. Most traditional queries are UDP 53, unless there's no response back, or there's a request to transfer to TCP 53. But most often it's UDP 53. Zone transfers also happen over TCP. So zone transfer, we're not going to get too deep into DNS, but there's a start of authority. There's an authoritative name server, and there might be one or more other name servers that are also in that same zone. They do file transfers to keep the records correct amongst the name servers. Those zone transfers happen on TCP port 53. Anyway, if you want to do DNS-y type stuff, NSLOOKUP is your tool, right? You guys have all used NSLOOKUP before? Okay. And then there's caching. So another thing, because there's cache poisoning attacks against DNS, but most DNS, it's not all that effective really anymore. But if my name server, so there's iterative queries and recursive queries, right? I think we'll get more into this later on. But a recursive query is if I'm not the authoritative name server for this zone, I'll look it up, right? I'll go on to the next, I'll refer on to the next name server. When I get the response back and respond to the client that wanted the DNS resolution, I'll cache that entry, right? And I'll cache that entry for as long as the DNS record that's held by the SOA, the start of authority, tells me, right? There's a TTL associated with that record, and that'll remain in cache. So the next time I get a name resolution, I don't have to go through the whole recursive query bit again. I can just respond to the clients, which is really nice because a lot of, like in a company, a lot of people are using the same hosts often, right? So having those cache queries really speeds things up. So there is a caching function and there's cache-only name servers too, right? There's name servers that they're not sort of authorities for any zone. They only do caching resolutions. They would just store the cache. So DNS, there's, essentially a traffic flow for DNS. The DNS itself, the way it's configured, the root domain is just a dot, right? The .com is not the root domain. That's a TLD. That's a top-level domain. So the .com, .net, whatever. There's also reverse DNS, which is the in-adder ARPA resolution. So if I know the IP address, but I don't know the DNS name, that would be a reverse DNS lookup. And I'd have to essentially you have to try to explain how you do it. NS lookup is the only way I do reverse IP address lookups. And you have to put it in the function. You basically set the IP address backwards in adder ARPA. .in-adder.arpa would get you resolution backwards. So anyway, reverse DNS lookups. They use the same protocols, UDP and TCP 53. It's just different types of queries. DNS weaknesses, so unreliable UDP protocol. DNS cache poisoning used to be a big deal. There's a lot of DNS implementations over the years that have been buggy. A lot of people set up zones and don't realize that they're allowing full zone transfers. So an NS lookup connect to the startup authority and just do an LS, right? Domain name, and you'll list all the domain records. That's essentially a zone transfer to your local system. So a lot of people set up, not a lot, sometimes people set up their DNS servers and allow anonymous zone transfers, right? That would be a bad thing because now I know every record. It's great for mapping and reconnaissance. I know every subdomain for this domain, along with its associated IP address. I know what to attack, potentially. DNS cache poisoning would be those caching functions. So if I could poison the cache to change www.microsoft to be my IP address, well then it would, all the traffic and I can make my server look the exact same, the users would have no idea. It would be very difficult for them to know that they're not communicating with the real Microsoft. That's an obvious one that, it's not easy to do, and but it is a potential risk. DNSSEC is one of the things that you could implement to protect so DNSSEC allows for authentication of domain name servers and the integrity of the responses. So, and it all uses PKI and encryption, digital signatures. If you want to know how to set up DNSSEC, you can do that. Most people don't have DNSSEC set up. I think most people don't know how to do it. I don't know how many DNS tests we've run over the last 10 years, and probably seen 5 that have had DNSSEC set up.
Yeah, that might be generous.
Yeah. So it's really uncommon to have it set up, but this is something that you could implement. HTTP and HTTPS, more protocols, Hypertext Transfer Protocol, port 80, and HTTPS. The secure method of the same protocol using 443. Now, HTTPS and SSL and TLS are not the same. HTTPS is the protocol that uses SSL and TLS. So they're different, but very closely related. A lot of times we mix those up and think that they're all the same thing. HTTP, HTTPS, BootP, DHCP, BootP, and DHCP. Most BootP implementations appear to have been replaced by DHCP, but it's the bootstrap protocol. So when my computer boots up, it may not know anything about the network or anything about communication. A BootP server would supply all this information so that it can communicate on the network including where to find its disk image potentially. DHCP works a lot the same way. There's a lot of different extensions I can apply with DHCP. You guys remember Win servers? You guys don't remember Win servers? Windows Internet Name System? It's the way we used to resolve NetBIOS names to IP addresses. That was the last time I actually configured a DHCP server, when we used to have Win servers. It used to be one of the things that you would supply in your DHCP. DHCP is just a lot more robust. You can assign DNS servers, all kinds of stuff with DHCP, but Win servers is for some reason that popped in my mind as one thing I used to assign with DHCP. Use the same ports, UDP, what is it, 67 and 68. Those will not transfer routers by default. Usually you'd have to set your routers to do that. So if you have a DHCP server trying to supply multiple subnets, you'll have to do some additional configuration. All right. We're doing well. Oh no, crap, we're late. I was just getting going too, you guys. All right, let's go through fast. Layer 1 cabling. These are the things that I was just having a casual conversation, loving life, and my LaCroix. All right, layer 1, we already talked about this is the simplest functions that happen at layer 1. Network cabling is here. Different things about network cabling that we'll need to know for the exam. EMI, electromagnetic interference. What I was talking about the cabling running over the light, that would be EMI. Crosstalk is when two signals are so close together, they're not shielded properly. You ever been on a telephone call? Back in the day, you'd be on a telephone call and you'd hear somebody else's conversation. That was an example of crosstalk. So it'd be essentially network communications jumping from one cable onto another, and that happens. Attenuation is the weakening of the signal over a period of time or distance, usually distance. So layer 1 cabling, twisted pair cabling. The twists, are supposed to protect us from EMI. The tighter the twists, the more the protection. So unshielded twisted pair and shielded twisted pair. You don't see shielded twisted pair really anymore. Most of it's unshielded twisted pair. Cables are classified according to categories and rated speed. The twisting and allows for more. And actually, it protects you more against crosstalk too. I don't think it does anything for you for attenuation, but EMI and crosstalk would be the twisting of the cables. The tighter the twisting, the better the cable, essentially. You'll need to know this a little bit. So Cat 1 cables, you'll never see those. Well, maybe you'll see them somewhere again. Cat 2, this is where these are my beautiful token ring networks running at 16 megabits per second. Cat 4, actually those would be Cat 3. Well, actually Cat 2s would run at 16. Cat 4, whatever. The only ones you see here are Cat 5, Cat 6, maybe, really. Telephone cables for Cat 3, I believe. Normal telephone cables for Cat 3s. This is maybe another one, maybe one that's better. So the category of the cable, the data rate, how far it goes, cable types. This will be just memorization. Functionally, the only ones you see, again, are probably Cat 5 and above for data. You might see some telephone networks, cables laying around still for their Cat 3. Other types of cabling, coaxial cabling. You can see what a coax cable looks like. We've all probably cut one at some point and looked at what it looks like. So you've got the copper wire, the insulation, the copper mesh, and the outside insulation. They are very resistant to EMI because of the shielding. And also there's not a lot of, I think it's more direct communication, just the way the cable has been configured, because it'll bounce around. The signals bounce around, but they really are contained by the shielding, and it's kind of this direct, as opposed to relying on the twisted pair. Two other types, thin net and thick net. Thick net cables, we used to, there's a vampire tap right there. That's how we used to tap into a thick net cable, because you'd have to actually, it was a vampire tap, so you'd have to screw down the top, and it would put copper or, teeth into and through the cable. And that's how you would have to communicate. This other one, the BNC connectors, that came a little bit later. And these are put together and just kind of twist, and they twist and lock together. But that's the way we connect these things. Fiber, the fiber optic theoretically has an infinite bandwidth because, in a prism, that's the picture there, you can segment or separate out a light into an infinite number of channels, each color representing a different channel. So light can carry information, whether it blinks or whatever. Long distances, completely immune to EMI, no crosstalk in fiber optic either. Multi-mode fiber carrier, single mode fiber carrier, you'll need to know the difference between those. Single mode, I guess you have a good diagram here for you for multi-mode and single mode. Single mode goes further. And then this is wave division multiplexing. So wave division multiplexing is essentially the same thing as what the prism is doing. So on one side, it's separating out, it's demultiplexing, and on the other side, it's multiplexing. Or depending on how you look at it, multiplexing and demultiplexing. That's what it looks like. Single strand of fiber, multiple channels. LAN technologies, Ethernet, most common local area network technology. We're still using it today. Traditionally, it was in a bus topology. A bus topology is just from here to there. It's just one straight topology, and everybody would connect onto it. That's what a bus topology looks like. Baseband, one channel, that you already knew that from before. Ethernet describes both layer 1 and layer 2. So if we take the types of cable and we lay it on top of Ethernet type, these Ethernet types, the first one is the speed, baseband. They're all going to be baseband because all of Ethernet is baseband. And then the type of cable. When you look at the Ethernet type, that's what that denotation is. That's the bandwidth, that's the cable type, half or full duplex. This is also another good thing to memorize. Typically the more current ones, I think, than the other ones. That first number, by the way, was the actual distance or speed. Distance. No? It was speed. I can't remember how we tied distance into cabling, but anyway, memorize this. I don't know, man, it's getting late. Carrier sense multiple access. So there was two ways to access an Ethernet network. There was either carrier sense multiple access, collision avoidance, or collision detection. Collision detection is the traditional Ethernet mode. Collision avoidance was like AppleTalk used collision avoidance. Wireless networks use collision avoidance. And the function is essentially like this. Monitor the network to see if there's any network traffic going on right now. If it's idle, wait in a random amount of time, and then begin your network transmission. That's collision detection. Collision avoidance was much more, what's the word I'm looking for? There's a lot more overhead with collision avoidance. So all Ethernet networks today are collision detection, unless you're running AppleTalk. I don't know anybody still running AppleTalk. ArcNet and Token Ring, these are both old technologies, legacy. I can't remember the last time I've seen them. But it's all a token passing network. So I can't communicate on the network unless I own the token, unless I have the token. Are they all leaving?
No, my battery died.
Your battery
I
died.
was hoping I could squeeze it out and it was just...
Well, if I would get talking faster. No collisions because it's a ring. It's a logical ring, a physical star topology. So this is how the network is laid out. It's a logical ring, so there is no collision. It all goes in one way. There's counter-rotating rings with FDDI because for redundancy, but a lot of times what people would do when they implemented FDDI networks is they just put them both into production. So then you lose all your redundancy, but you have twice the speed. ArcNet, Token Ring. Oh, I haven't even gotten to FDDI yet. There's FDDI. ArcNet 2.5 megabits per second. Star topology, physical star. So a star topology is a central system, and everybody connects to it. That's your traditional Ethernet now that you see with your switches. Token Ring and FDDI and a lot of these logical ring were physical star networks. Token ring had what was called a multi-station access unit or a multi-access unit. And in that, the circuitry would be in this one, out this one, in this one, out this one. So logically, it became a ring, but physically, it was a star. Everything connected to it like it was a switch. City, another fiber network. This is a local area network. This is the one that had the two counter-rotating rings, but typically we set them up. One was for fault tolerance, but we'd get them both going active, so you'd have 200 megabits per second. There's a bus topology, logical string, physical string. It's just a bus. This would be the vampire taps or the BNC connections. That was just back in these days. The tree topology, this is more a central unit that kind of controls. It's a polling type of technology where I'm only going to allow you to talk, and I'll allow you to talk. Do you want to talk? I mean, it's that type of topology. That's a one central unit. This would be more like mainframe-ish type communications, dumb terminals, things like that. This is that logical ring, that MAU and MSAU, that's the multi-station access unit, the multi-access unit. That's token ring networks. It's a logical ring, physical star topology. The star topology, this is what we're all used to. This is what we've got in most of our network closets today. Just everybody connects to a switch or a hub. This is an exam warning, just, the difference between physical and logical. So knowing what a logical ring and a physical star is, and that's just the warning. And we've got mesh, full mesh and partial mesh. Now, full mesh network, a lot of overhead in a full mesh network, right? Because it's a lot of cabling, it's a lot of coordination, but a lot of redundancy, right? And if any one hub, any one system goes down in a full mesh network, it doesn't affect the network at all. There's still redundant paths through other systems than a partial mesh network. So we use this for high availability. Very rare to see a full mesh network employed in people's environments. That's it. So, hallelujah. We left off on page 253. You guys get a whole week off. And if you have any questions, I'll be here for another 30 seconds. So, thank you guys.
Thank you.
Like,